This is a continuation of the notes from Thursday. If you weren't there or forgot your notes, you can do this on loose leaf or print it off from Schoology. We were talking about how quickly reactions take place, and we were writing rate laws expressions. So, for example, the rate is equal to the rate constant K, which is temperature dependent, and it changes for each reaction, times the concentration of the reactants raised to whatever order they are. And the order looks at how exactly, like how much does a change in the concentration of the reactants affect the rate. Now the order could be 0, 1, 2, 3, 4, 5. We're going to look at exactly what those orders are, like 1, 2, 3, 0, 1, 2, and see exactly how does a change in concentration of that reactant affect the rate. So here's an example. Consider this equation. A plus 2B plus C makes product. The rate law is rate is equal to K times A is second order and B is first order. Now you notice that C is not a part of this, which means what order must it be? It has to be 0 order, because anything raised to the power of 0 is just 1, and you can cancel it out of the rate law expression. Okay, so let's see exactly how a second or first order affects the rate. So first we need to determine the value of K by plugging in the data from the first experiment. We have the rate, we have the concentration of A and B and C. We're able to find K. So we're just going to plug this into the rate law expression. So we have rate is 0.004 is equal to K, what we're trying to solve, times concentration of A, which is squared, times concentration of B raised to the first power. And the concentration of C can be left out because that's 0 order, and anything raised to 0 is 1. So solving for K, you should get 0.5. Now, we also want to include the units of K. This is where it can get a little trickier. So if I were to write this equation, but instead of plugging in numbers, plugging in the units for each variable, the rate is molarity over seconds. K is what we're trying to solve for in units. The concentration of A is molarity, but that's squared. Concentration of B is also molarity raised to the first power. So we basically have molarity over seconds is equal to K times molarity cubed. Well, to solve for K, we have to divide both sides by molarity cubed. So that's essentially molarity over seconds times 1 over molarity cubed. Well, molarity divided by molarity cubed is the same thing as 1 over molarity squared. So this could be the units of 1 over molarity squared seconds, or molarity to the -2 seconds to the -1. We're going to go through after this how to determine the units on K. There's a pattern that will make it a little bit easier. Okay, so let's see. How will a change in something that is second order affect the rate? In order to do that, we need to change the concentration of A, but we don't want to change the concentration of B or C because we only want to focus on how a second order reactant and its change in concentration will affect the rate. So I'm just going to double A, concentration of A, but I'm going to keep the concentration of B and C the same and see how that affects the rate. So if I were to plug these values into the rate expression, as well as the K I know is now 0.5, I can solve for the rate. So basically what I'm doing is rate is equal to 0.5 times 0.4 squared times 0.2. And I find the rate is 0.016 molarity per second. So if you look at how that changed, how is 0.016 compared to 0.004? It's 4 times as big. So if you notice, if we take A, which is second order, and when the concentration of A doubles, the rate will quadruple. It'll go up by a factor of 4. That makes sense. So if we think about how this rate law expression works, if the concentration of A was doubled, so 2, and it's second order, which means it's raised to the second power, that would equal a rate of 4 times as big as what it used to be. 2 squared is 4. Let's look at B. Now B is first order. Let's see how a change in first order reactants affects the rate. It'd be easiest if we double B to 0.4, but we keep A and C the same. And you could keep it, let's just keep this 0.4. And we'll see what the new rate is. So we're plugging these values into the rate law expression, including K is 0.5. So 0.5 times 0.4 squared times 0.4 is equal to 0.032. Now, if we compare that to how the rate changed from the previous trial, that went up by a factor of 2. So whenever you have something that is first order and the concentration of that reactant doubles, you can see that the rate will also double. That makes sense because, again, if we look back to the equation and the power that B is, which is its order, if we double the concentration of B and it's first order, so raised to the power of 1, how will that affect the rate? It'll equal a rate that is twice as big, because 2 to the first power is 2. Now, C, on the other hand, is 0 order. We don't even include it in the rate law expression because anything raised to the 0 power is 1. So you can probably imagine how that'll affect the rate, if at all. But we can, use our numbers and see and prove how that'll affect the rate. So if the concentration of C doubles to 0.4, but we keep the concentration of B and A the same, let's calculate the new rate. Well, C isn't even part of that. 0.4 raised to 0 is just 1. The rate should stay the same at 0.032. So when the concentration of C doubles because it's 0 order, it has no effect on the rate. The rate will stay the same. Again, because if we double the concentration of C, so 2, raised to the 0 order, that'll equal 1. The rate won't change. Okay. Imagine we have something that's third order. How will that affect the rate? Well, if the concentration of that third order doubles, take a second, think about how would that affect the rate? Well, if we double something that's third order, so its concentration is doubled and it's raised to the power of the third, then the rate should increase by a factor of 8 times what it used to be. So it'd be 8 times bigger. All right, let's figure out the units on K and what the trend is. So remember, our rate law expression is rate is equal to K times the concentration of A raised to whatever order it is. Now, there might be other reactants as well. So in that case, this had 2 reactants in the rate law expression. One was second order, one was first order. That tells us that the overall order of the entire reaction is 3 because 2 plus 1 is 3. So that's what we're talking about here. That would be the order that I'm talking about right here, the order of the entire reaction. Okay, so let's say it's 0 order. I'm going to put units in for the equation. So the rate is usually molarity per second. K is what we're trying to find the units of. Concentration of A is in molarity, and it's raised to the 0 order. So it must be the units on K. Well, anything raised to the 0 order is just 1, so that basically just cancels out. So K is molarity over seconds, or in other words, molarity raised times seconds to the -1. If something is first order of reaction, molarity over seconds equal to K times molarity raised to the first. If I were to solve for K, I would have to take molarity over seconds times 1 over molarity, dividing both sides by molarity. So molarity divided by molarity cancels. My units on K is just 1 over seconds. Or in other words, seconds to the negative 1. If my reaction is second order, that's molarity over seconds is equal to K times molarity squared. Solving for the units on K, we'd have to divide both sides by molarity squared. So that's molarity over seconds times 1 over molarity squared. Well, molarity divided by molarity squared is 1 over molarity. So the units on K are basically 1 over molarity seconds, or molarity to the negative 1 seconds to the negative 1. If it's a third order reaction, molarity over seconds is equal to K molarity cubed. Solving for K, molarity over seconds times 1 over molarity cubed. Molarity divided by molarity cubed is 1 over molarity seconds. So essentially this is molarity raised to the negative 2 seconds to the negative 1. Hopefully you're seeing the trend here. So you could see that the fourth order reaction is going to be molarity negative 3 seconds negative 1. If we were to look at the units on K for a fifth order reaction, that'd be molarity to negative 4 seconds to negative 1. So basically, if you're just trying to memorize the units on K, if you have a first order reaction, it's just seconds to negative 1. Once you start going to second order, start subtracting. 2 minus 1 will tell you what power the molarity to the negative is. 3, third order, would be to the negative 2. Fourth order would be to the negative 3. Or you could solve for, of course, solve for the units on K the old-fashioned way. Okay, I'm actually going to break this up. I don't want to make a huge mega video of notes. So I'm going to pause the video here. And I'm going to make a new one where we go through some practice of determining the order of each reactant, writing the rate law expression, and determining the units on K. So stay tuned for another video.